So now you might be wondering why I'm putting more structure on categories. And the reason turns out to be that, well, our goal is to explore cohomology a bit. And the reason why cohomology is so popular among, well, topologists, mathematicians in general, whatever, is that they indeed do not only form groups or like graded groups or whatever, but they actually form rings. And categories, or at least the categories we have just defined, turn out to be some generalization of rings where we are not able to multiply everything anymore. So to illustrate this, I thought it might be useful to look at, well, all of the categories we have discussed above in the special case where we have only one object. So what happens then? And, well, first case, normal category. Well, then C is given by, well, the set objects of C, which is just the set with one element. And then we have exactly one set of morphisms. So we have morphisms in C from dot to dot, which I guess we can just call A. And now what sort of structure do we have on A? Well, we have a couple of things. We have the identity on C is an element of A. Then we have composition is a map from A cross A to A. Associative, together with the property that, well, the identity composed with anything is that same thing composed with the identity, is, well, F. And these axioms sort of look familiar. They look kind of like the group axioms, right? Except we're missing one key ingredient, but we don't have inverses. Or we don't necessarily have inverses. Which means that A is, well, not a group, but sort of the next more general bit. A is a monoid. Which means that C is sort of completely determined by its monoid. So we can sort of say that categories with one object are sort of in bijection to monoids. And, well, this is also where the word monoid comes from, or at least I choose to believe that this is where it comes from, because mono means one. So yeah, one object categories. Okay, next thing. We have abelian categories. We again have, well, the same thing. We have just one object, and therefore the whole category is just defined by what we take the Hom set of that object to be. So we have morphisms from dot to dot, which we again call A. And now what do we have on A? Well, firstly, since it's an abelian category, A is an abelian group. But secondly, we have an operation, again the composition, from A cross A to A, which is associative. It respects the identity. And it's bilinear, meaning that we have F plus G composed with H is equal to F composed with H plus G composed with H, and the same thing for, well, the other thing, meaning that we have a distributive law. So does that remind you of anything? Yes, it means that A is a ring. It doesn't need to be commutative, but it's just any kind of ring. So now for K linear categories. blah 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 blah. We have A is a ring, but we have more than that because A is a k-vector space. Just by definition of k-linear category. And we have that the ring multiplication, or I guess the composition, is k bilinear. And what does this now sound like? A vector space where you can also multiply elements in such a way that it forms a ring, and so that sort of the k-linear structure and the ring structure are compatible. This is precisely one of the definition of a k-algebra. Next thing, graded k-linear category. Well, we saw A is a k-algebra, but A is also graded, or a graded vector space. Namely, A is the direct sum over all integers of an, and we have that the composition is of degree 0, meaning that, well, sort of f composed with g has degree deg f plus deg g, where, well, when f and g are homogeneous, meaning that they are indeed contained in one of the an. So, and it probably doesn't surprise you to hear this, but this means that A is not only a k-algebra, but a graded k-algebra. And now, last but not least, DG category. Well, we have, again, A is a graded k-algebra. But we have more. We have a map D from A to A, such that A increases degrees. So if we restrict A to an, then it maps an to an plus 1. It's k-linear, but not a-linear. And we have the Leibniz rule, meaning that d applied to fg is dfg plus minus 1 to the degree f times f dg. And I guess if everything is concentrated in degree 0, this really is just the product rule. This means that A satisfies the axiom of, well, applying analogy to the previous names, A is a dg-algebra. So overall we can see that if we have just one object in our category, we can compose all arrows, meaning that we have a total multiplication operation, which, if we also have other operations, sort of plays nicely with these, so that we have, well, a monoid or a ring or some generalized algebra structure. And that makes these categories that I've defined the sort of natural object to study if you want to step up your cohomology game.